Okay, welcome everyone. So one of the basic trips and problems I saw when students start to submit their assignments in general is understanding what exactly they should deliver in the final result. So you need to understand what exactly we want to achieve as an outcome from the assignment. The output should be an image. Okay, not figure, not a plot, image. Okay, meaning that if you are reading an image from the hard drive, you need to save the processed image to the hard drive. Okay, no screenshots, no figure save. Okay, if you are using any of the techniques of screenshots or figure save, then you are not saving an image. Okay, the actual results of the image will be only appear when you save it back to the hard drive using the proper image save technique. How you can save any array back as an image to the hard drive? You can have two techniques, or you can do this in two ways. Actually, more than two, but for now, using the libraries we learned so far, we have two techniques. The first one, from the PyBlot library, there is imsave command. Okay, this one, take the name of the image as an input, then the array you want to save it, then the type of the image. Is it grayscale image, color image, whatever the type of image you are working with. So as you can see, yeah, this is the CMAP, which is the format you want to save to. Okay, so if you want, for example, to work on one of the assignments you are working with, after you show it or after you do whatever you want to do with it, you can easily go here and press plt dot image save. Where is it? Then the name of the frame, dot whatever the extension you are working with. Mostly I like to work with the extension PNG, because PNG shows exactly whatever you have without any compression or any processing. If you are using JPEG or any of the other formats, the saved version from the image will be processed, compressed, or shaped, or whatever the technique they are using, which means the image is not correctly saved. Okay, so the only two formats that proper for this technique is the PNG and the PNP. The PNP doesn't do any kind of processing to the image. Okay, which means the image size will be too large, but it's pure. Whatever you get it, it will save it to the hard drive without any processing. PNG make a little bit processing to it to make it more portable and work well with moving from one device to another. Then you have to write the name of the file or the array you want to save. In this example, the array here is npimage. Okay, then after I execute this image or this array will be saved to this memory location on my hard drive. Now I can add it to my zip file or to my submission to the website. Okay, most of you don't do that. Most of you do what? Yeah, so assume that this is the image that you got after processing. You take screenshot for that. And you tell me this is the output. No, this is not the output. So if you submit this screenshot, it's wrong. It's not the correct one. Why? For several reasons. One of them, the pixel value that you can see here is adjusted to the screen value. So if you try to expand it, you see the image become what? Bigger. If you shrink this, it will be smaller. What is the correct image size? The bigger version or the smaller version? None. None of them are correct. So the only way to achieve the correct one is to save it first. Use the save command, image save command from the byplot library to make sure you are saving it correctly. Okay? Yes.
Can we save from the?
No. Actually, this is the same issue. It's not a figure. If you save it from here, you are saving it as a figure. This is the second thing that you don't do it. So no screenshots, no figure save. Save it as image. Is it clear? So if I saw any kind of submission which is including screenshot or figure save, this will not be considered as a correct submission. Okay? I'm giving you an image as an input, then I'm expecting an image from as an output. Don't give me figures, don't give me screenshots. None of those are images. Okay? Is that clear? The second one, if you don't like to use this technique of the byplot, there is another technique through the PIL library, which is image.save. Again, this is doing the same exact thing that will happen through the Matplotlib library. In this case, you need to convert. You need to convert the image. It's not finished. This is not. Actually, you know what? Let me open the code. So, if I assume that this is the image or the array I want to save, I need to convert this array first to an image object. Remember last time when we discussed the PIL, we said that the PIL library read the data from the hard drive and convert it to image objects, not array, image objects. Okay? Then I can extract the array from this image object. Here, I'm doing the opposite. Instead of extracting the array from the image objects, no, I'm converting back the array to image objects. So here, I will convert this array to an image object. Then you can save it. im.save, then the file, name of the file you want to name. Okay? Again, I don't prefer the JPEG. I highly recommend to use the PNG. Okay? So either way are okay with me. You want to use this PIL technique, okay, good. You want to use the plot technique, the IM-save, okay with me, okay? Is there any other method that can be used to do the job? Yes, using, for example, the OpenCV. But remember, what is the constraint that we add at the beginning of the semester? No OpenCV should be used, okay? Here, I want you first to work from scratch by yourself. So don't use the OpenCV, okay? So for now, those are the two available techniques for you to save the image back to the hard drive, okay? Is this clear? Last time we start talking about one of the most important process or operation in the computer vision and image processing in general, which is the convolution process. And we explain how exactly can we do the convolution and what is the difference between convolution and cross correlation. What's the difference?
It's like how you filter each pixel.
5 marks bonus.
I guess.
Reversing filter values in the filter.
Okay, so the convolution is a cross correlation with double flipping the filter horizontally and vertically. So if you flip the filter first horizontally, then vertically, you will apply the cross correlation. Okay, so they are similar. The only difference is how we apply the filter. Remember these steps that we did last time? Horizontal, vertical, then apply. That what differentiate the convolution from the cross correlation. With the cross correlation, I'm doing nothing, just apply the filter directly to the image. Convolution means flip, flip, then apply. Okay? Don't fall in this trap. Then we start to learn about, the types, how we can apply convolution to the image, and we learn how we can extract the output image from this process, and we came up to this equation where n is the dimension of the input image, f is the dimension of the filter, b is the dimension of the padding. Remind me, refresh my memory, what is the padding? To what?
Image
Why?
to enhance the quality, to remain the pixel size.
Exactly. To rename or keep the size of the output equal the size of the input. So it's extra pixels that you add to the input image to sustain the size. As we stated last time in this example, we said that if the input is 7 by 7 and we apply 3 by 3 filter, the default output will be 5 by 5. So what if I want the output to be also 7 by 7? In this case, I will add 1 extra pixel from each direction. In this case, the input size will be 9 by 9. When I apply the 3 by 3, the output will be 7 by 7 rather than 5 by 5. So the input size will equal the output size. That's by using the padding technique. And we stated that the equation for the padding or for the output, if we are using padding, is n minus f plus 1 plus 2b, where b is the number of pixels we add in the padding, n is the size of the input image, f is the size of our filter. Also, last time I asked you a question. What if we apply or we didn't shift the filter one place, like in all the examples we had last time? We are keep shifting by one place, right? What if we shift with more than one pixel or one place? Can we calculate the output of this process or extract equation for this flexible shifting?
Yeah.
Okay. Okay, we have two opinions right now. Who said yes? Okay, who agree with that? Who said no? Who agree with that? What's wrong? You didn't register for voting or what?
I'll say yes.
Okay, we have one vote for yes.
Maybe causes asymmetric.
Maybe?
Asymmetric, like some gaps will be there.
Okay, now we have two votes, yes or no? Which one we choose? No, so you are saying no. We have two votes for no now. So we have three votes no and two votes for yes. What do you say?
No.
No.
Say no.
No. I would say
Okay, so we have almost a majority of no. So we can't find the equation for the output. That's what you are all saying, right? Unfortunately, all of you are wrong. We can find the equation. And the relation for this equation will be this one. So assume that we are doing a shift with more than one pixel. As last time we stated, we are calling this stride step. So instead of moving with one pixel, I'm moving two or more. So if I'm assuming that I have a stride of two, in this case, if this is the first filter or the first position, I will shift by two. So this one will be here. Then I will shift by two more. So I will be here. Okay. In this case, I'm having 7 by 7 as an input. The output in this case will be 1, 2, 3. So it will be 3 by 3. Okay. Now, how can I relate this to this to this to produce this? This said, we can relate them with this equation. So let's apply this equation and see how it will work. N is the size of the input image. So here it's 7. F is the size of my filter, which is 3. B is the number of padding pixels. Did we do any padding here? So 0. Divided over S, which is our stride, plus 1. Let's do the calculation. 7 minus 3 equal 4 over 2 equal
2.
plus 1,
2 even.
which is the output. Okay? So we can have a solid equation to calculate the size of the output image for any number of input pixel, any number of filter size, any number of pixel padding, and any number of stride. Okay? Now, can we have stride more than 2, like 3?
Yes.
So I will start from here. This is my starting point. Then I will shift 3 pixels. That's what the meaning of the stride. The number of pixels you'll shift. So I will shift 3 pixels. So 1, 2, 3, and shift. Can I shift more?
No.
So this case, or in this case, I'm generating only 2 outputs or 2 pixels. So the output in this case will be only 2 by 2. Let's check the equation. Will it apply in this case or no? N equal 7 minus F, which is pixels or the padding is 0 over plus 1. So 7 minus 3 equal over 3, 1 and 1/3 plus 1, 2 and 1/3. Can we have 1/3 pixel? No. So if we round this, it will be what? So it will be 2 by 2. Does this make sense? Yes. Why? Because we ignored one column and one row. If you keep doing this over the rows as well, you will find that you will ignore that and will ignore that. And this ignorance will bring this. That's why we have to cancel this, and it will be 2 by 2. What does this mean? It means that I can't use any value of stride I would like. I need to be careful when I choose the stride value to guarantee that I'm ignoring any pixels in my image, because any pixel include information. If I ignored it, this means I'm removing information. I'm throwing it in the ocean. Okay, so this will become useless. I'm reducing the amount of information I can use. Okay, so when you use or you change the stride value, be so careful, okay, because it can cause data loss in your output. So as you can see, when the stride equal 1, it will be 5 by 5, exactly 5 by 5. So I don't lose any information. If the stride equal 2, it's 3 by 3. If the stride equal 3, now I will start to have a data loss. Okay? That's why we always try to add the padding to solve this problem. Okay? So we can add extra padding here to solve this 3 by 3, or sorry, the 3 pixel shift issue. Okay? So we always try to add the padding size to be proportional to our filter, to guarantee that we will not lose any shift or any data we have in our image. Okay? So this equation should be written in your brain. Don't lose it. Okay. Last time as well, we learned about several types of filtering, which is the regular mean filter, and we stated that the mean filter is used to blur or to find the mean or the average value of the given image. And we said we can play around with this filter to even sharpen the image, as we stated here on those equations. So we can have a sharpened addition from this filter. Okay. Also, we stated two conditions for the filter to be considered as a mean filter. What are those two conditions? The size of the filter must be odd, which means 3 by 3, 5 by 5, 7 by 7, 9 by 9. It can't be even. The second thing, the sum of all values in the filter must equal 1. Okay? If any filter satisfies the two conditions, we can consider this filter as a mean filter. Does this apply on any filter in general? Like, can I have a filter that do other things that satisfy other conditions than those? Yes. Okay, and we will see maybe by the end of today or next week another type of filter that do different functions. Based on that, we start to introduce another filter, which is this one. This is what we call the Gaussian filter. The Gaussian filter is a discrete filter that approximates the continuous bell shape, regular bell shape. Okay? The regular bell shape has an area under the curve equal what is the area under the curve for the bell shape? Is it?
Radius of curvature.
So, if you integrate this, what is the equation for this one first? Anyone know what the equation for the bell shape? What is it? Parabola?
UAG.
Come on, guys. What is the equation for the Gaussian? What is the equation of the normal distribution? One over square root of 2 pi sigma e power minus x minus mu all square over sigma. Okay, so we can simplify this into e power minus x squared multiplied by some constant for normalization. So if I want to find the area under this curve, what it will be? How I can find the area under the curve? Integration. So if you integrate this from minus infinity to infinity with respect to x, the result will be what?
Yeah.
Which is what? Which is what? One. The area under the curve for the normal distribution is 1. What is the property of any BDF? Probability density function. We discussed this last week. What are the properties of the any BDF function? A function can be considered as a BDF if it satisfies the 3 conditions. Satisfy the 3 conditions. The value at any point must be greater than 0. The value of any point must be less than 1. The summation of all values must be 1. This is for discrete. If we are talking about continuous, this means the integration of f of x dx must equal 1. Okay? So those are the conditions for the BDF. Now, this is a BDF. This is a BDF already. Okay? It's a normal distribution. So it's a probability density function by default. So the sum or the integration of this under this curve must be 1. Okay? That's why we are considering this a type of mean filtering. In this case, we have the highest value in the middle. Then on the main sides, it's reduced a little bit. On the diagonals, it reduced more. So it looks like a bell. For normalization purpose, the sum of all the elements here must equal 1. So if you sum all those elements, it will become 16. That's why we divide over 1 over 16. Okay? So this filter satisfies the two conditions we just explained. First, it's 3 by 3. The sum of all values here, of course, after we divide over 16, it will be 1. That's why we consider this a plural filter or a mean filter. Okay? And last time we showed the difference between those two images. This is the output of the regular filter, and this is the output of the Gaussian filter. Now, the question should be, why the output of the Gaussian filter looks better than the output of the traditional mean filter? Why this looks blurry? Yes, but it shows more details in the image rather than here. This one looks hesitating a little bit. This one, it's blurry, but more clear. So I can still see some details rather than here. So the question is, why? Why I can have this property for the Gaussian? To understand this a little bit, we will consider this regular mean filter, or call it a boxy filter. Why it's called boxy filter? Because if we apply it to a regular image which has only one value, it will produce a box. So if you look to it in 1D, that's how it will look like. All the values here are fixed and no values around that. That's why we call it a box filter or a boxy filter. How about the Gaussian? Will it look the same? Look to it here. That's how it will look like. It's have a high value in the middle, then on the sides start to have lower, and diagonally it's much lower. Can we have any explanation for that? Actually, we have. To understand this in more details, let's have small introduction to the frequency domain. What is the frequency domain? Assume that you have any signal in time. Something like this. So this is the time, and this is the value. Consider it an audio signal. Okay? This signal is captured by a microphone. Can we understand or can we hear all the component of this signal or no? Why?
Some of it your ears won't pick up, or whatever the. Are you asking like, can we hear it, or like, can the machine hear it?
No, can we as humans?
Yeah, no, we won't pick up everything
Why?
because of just the quality of our ears.
Exactly. So our ears have limitations. What are the limitations? Our ears can understand frequencies or signals with frequencies from 20 Hertz to 20 kilohertz only. Anything below that, we will not be able to hear it. Anything beyond that, you will not be able to hear it. Okay? Plus, each band of this requires specific speaker to produce. This is a completely different story. Like this one require a base, this one require a subwoofer, and each one of them should be different. But this is not my problem right now. The question is, how can I analyze this signal to see if it's within our hearing range or no? For that purpose, we are doing something called Fourier transform. Fourier transform is a mathematical technique which can be defined using those equations. I will not go through this in more details, okay? Because this is a high-end math. I'm not sure if any of you have it before. Did any of you cover the Fourier before?
During high school,
During what?
during my intermediate,
High school?
yes, +2.
Okay. I doubt that it's during high school because that's impossible, but that's okay. Mostly this is covered in the junior level or for university, not high schools. High school, that's impossible.
There is a chapter called Fourier transforms, so there be.
Anyway, I'll not argue for that.
Okay.
Now, what Fourier is doing, it transforms the signal from something called time domain in another thing called frequency domain. What is the meaning of frequency domain? It means that this axis, instead of being the time, I'm having another axis will be my frequency, omega. Omega is very well known that it equal to pi f, and f is our frequency, which is in hertz. So using the Fourier transform can convert this to this domain where I can see the basic components, frequency component in my segment. So for example, this one will have basic component here, and one here, and one here. Here, for example, at 10 hertz, this is at 20, and this is at 30, and the smaller, lower value. This means that this signal, basic component for it at this point. After that, the higher frequency reduce. Now, if I want to extract this signal only from this given input, I need to apply something called low pass filter. So the low pass filter is a kind of window that isolate the required frequency or frequency ranges to extract it from the given input signal. Okay? Filter is a technique, the word filter in general, meaning a technique to isolate specific frequency or frequency ranges from a given input signals. How I can explain this in this frequency domain plot? If the window I'm trying to isolate, starting from zero frequency, and going up to some specific limit, this is called low pass filter. It started from higher range, like 10 kilohertz, and going up to infinity. This is called high pass filter. Again, this is omega. It starts at a specific frequency and stop as another frequency. We are calling this band pass filter. So we have three types of filter. First one is low pass. Another one is high pass. The third one is band pass. So the band pass allow some part, ignore the others. Low pass allow the low frequencies and ignore the high. High pass allow the high, ignore the low. Okay? Are those the only 3 types of the filters? No, there are more. So this is regarding the given 2D or regular signal. For the images, can we have the same thing? The answer is yes. Now, what exactly are the high frequency components in the image and what the low frequency components in the image? Images. The high frequency components, leave this for now. The high frequency components are the edges. The low frequency components, the area that has similar characteristic or similar color. So this area is low frequency. Now, if I calculate the Fourier transform for the image, how it will look like look like this. So this is the Fourier transform for the image. For the regular signal, I'm having only one dimension, which is t. So I convert it to only one dimension, omega. For the image, it's 2D. 2D, x and y. Right? Remember this from last time? So for the frequency, I will have two frequency axes, omega 1 and omega 2. The center of the frequencies in the middle. So this is the origin of 0 and 0. 0 frequency 1, 0 frequency 2. Here the origin where? So for the frequency component, the origin in the middle. For the image, the origin on the side. Now, I want to apply the concept of frequencies I just explained in signals here. If I want to design a low pass filter, this means I will stop or allow the frequencies next to the 0 and block anything far. So that's what we call low pass filter. I want to pass the high frequency component, I will do the opposite. If I want to do band pass, then I will choose the range and apply it and stop the others. Now, if we look to any point here in this frequency component, what it will look like? That's how it will look like. So these points in the middle, as you can see, it has unique frequency. So black, white, black, white, black, white. So this is single tone. And because this is on this axis, it's what? Vertical. On the other axis, it will be horizontal. If the point in the middle, it will be depending on the direction, diagonal, on this side or on this side, depending on where you are taking the sample. The most important thing that it's each point is uni frequency. has only one frequency component. Okay? Now, if I want to filter the image, simply mask this with this. What is the value here in the black area? Zero. So all those are zeros. What is the value here in the white area? Or logical 1. So if you multiply this time this, what will happen? The thing will multiply with the 0 will be 0. The thing will multiply with the 1 will stay as it is. So that's what we'll have. Regular multiplication. Multiply the filter times the frequency domain. It will give you the filter image. Now, what if we return this back to the time domain again, or the special domain as we call it? That's what we'll get. See how it looks like? Now, what we did now is a multiplication process, but in the frequency domain or the Fourier domain. Now, this multiplication in the Fourier domain is exactly equivalent to convolution in the time domain. Remember the convolution process that we keep talking about last time and today in the beginning? This multiplication in the frequency domain equivalent to the convolution in the time domain or the spatial domain. So this is what we did is nothing but a convolution in the frequency domain, sorry, in the time domain. Okay? So this is exactly similar to applying convolution filter to the image. Shape of that filter. What is the filter that I can apply to this image to give me the same effect of this? This said, let's analyze it. So we apply the Boxy filter. Remember this Boxy filter? Which is this one. This is the same filter. The frequency domain representation of this will be the sinc function. What is the sinc function? Anyone know what is the sinc function? Sine x over x. Okay, so the frequency representation of the box filter will be sinc function. If I apply perfect filter, remember this is the perfect filter, right? That remove all the high frequency components and use only the low ones. The Fourier inverse of that will be sinc. So this image that I just saw is a convolution between the regular image and sinc. So the perfect filter is not our best option. How about the Gaussian? This said, the Gaussian filter in the time domain will be converted to Gaussian also in the frequency domain. So Gaussian here equal Gaussian here. That's why the Gaussian behave better. Why? Because it remains part of the high frequencies, which make the image more smooth. Okay? So the effect of the Gaussian come from the point that it keep part of the high frequency components to make the image still visible and has some details. Okay? That's why the Gaussian filter work better than the box filter or the ideal filter. Here is a small comparison actually between both of them. So this is the sync filter. If we apply it to the image, that's what we got. Remember, that's what we have here. So it's exactly the same. See? So this is the sync filter. You see how it will look like? It's horrible. But it's the best, or the ideal, not best, the ideal low pass filter. On the other hand, if we apply the Gaussian, that's what we got. Okay? Now, what is the equation for this Gaussian in 2D? This is the equation of the Gaussian for 2D. Bell shape. 1 over 2 pi sigma square times e power minus x square plus y square over 2 sigma square. The shape of the filter is like this. If you look or try to plot it as an image, that's how it will look like. All this area is 0, so it's black. The area that above the 0 will be start to gray and go to the middle, which is normalized to be 1. Okay? How we describe the filter or the Gaussian filter? We describe it with one thing or two things to be more accurate. First, the filter size. This filter as an example. What is the size of it?
Still odd.
Should be. So what is this size? I hear something from here.
5 by 5. 5 by 5.
Yes, 5 by 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is 5 by 5. Okay? The other thing that we describe the filter with, the sigma, which explain or describe the width of this white area. Okay? So, for example, assume that we have this input image. This filter is a Gaussian filter. The sigma value of it is 1 pixel. You see how small it is? When we apply it here, the image becomes more somehow blurry, but it has more details. If you increase the value of sigma, it becomes 5 pixels. So you see here it become more blurry, but again you can see the object. Here it's 10 pixels. Here it's 30 pixels. Can we apply more sigma on the same filter size? Like, can I apply the same filter size like this? Same size, and I apply sigma equal 50, an example. Can I? Yes. Okay. Who agree with that?
No.
Why?
I mean, at some point, it's just gonna be, you're gonna get back to the epoxy filter.
Exactly. So if we keep increase the size of the sigma value, this area all will be what? Almost 1. So you will get a full white. Okay? So it will look like the boxy filter. So there is a relation between the sigma value and the filter size. Those are related to each other. Within some specific filter size, you need to choose the appropriate sigma for that. And we will come to visit this point again when we discuss the features. Feature extraction. This point is really important at that moment. Okay? But for now, just put it in your brain that the value of the sigma is related to the filter size. For a specific filter size, I need specific sigma value. Just for your knowledge, the relation between them is the 6 sigma rule. Did anyone hear this word before? 6 sigma? The area under the normal distribution curve with the width of 6 sigma, including 99.9% of the power of the sigma. Okay? So we always try to make the size of the filter bigger than this 6 sigma. Okay? If it's lower than the 6 sigma, then the filter will mostly be white. Okay? Again, we'll come to visit this part back when we discuss about the feature extraction. Okay? So now it's more clear why the Gaussian filter is better than the regular boxy filter for blurring or for averaging the image. Okay? So if I give you now an image and I asked you to find the average of this image, which filter you will use? You will use this or this? Okay, so the Gaussian filter will be automatically the filter that will be used in many applications. Okay, so this Gaussian filter actually has some properties. What are these properties? First, it acts as a low-pass filter. Acts, but it's not an ideal low-pass filter. It removes some of the high-frequency components, but retain or remain part of them for good visualization. Second, if you convoluted two Gaussian filters, the output is Gaussian. So the Fourier transform of the Gaussian filter is Gaussian. The convolution between two Gaussian filters is Gaussian. So if you have two Gaussian filters, each one of them of standard deviation sigma, and convoluted them together, so if this is sigma and this is sigma, the standard deviation of this one will be sigma square root of 2. Okay? So one more Gaussian. Gaussian with Gaussian will give you another Gaussian. Okay, that's why we always prefer to work with the Gaussian filter. So this is the Gaussian filter applied to the image. You see how it looks like? This is the frequency representation. So instead of boxed, no, I'm applying a Gaussian representation. You see the image, how smooth it is? So if we compare it to this one, you see? This is too hesitating. This one, smooth. The other one is an ideal filter. This one is a Gaussian filter. Okay? Any questions? So, remember the process that we applied before for sharpening, but we applied with what? With the regular mean filter. Now we can play the same game with the Gaussian rather than the regular filter. So I can apply Gaussian filter to the image, subtract this from this, the output will be what? When I subtract image from the smooth version, the output will be what?
Clear.
I hear something.
Sharp.
Edges. So this is smooth. So this includes edges. This without edges. So remove this from this. The remaining is the edge. Now I can add this back to the image with a specific weight, whatever the weight it is. In this case, I'm having a sharpened version. Okay. Now this one can be the filter version of the image. So I can apply fluid version, or this is Gaussian filter. Then do the math as we did for last time. In this case, I can generate a newer sharpened version of the image. Now, if you did it for the filter itself, so this is the filter. It's 1 minus alpha times the original. So this is the impulses or the scale version minus the filter scaled also will give you a sharpened filter. So that's exactly what we got. So I can extract this filter directly and apply to the image. Or of course you can apply the map using this technique. Okay. So this is what we had and show last time. Okay. Now, if we apply it to a given image like this is the unfiltered part, and this is, as you can see, the filter part. The difference is so clear. The filter part is so sharp. This one is, the edges are fluid. So you can't make the separation between them. For the other one, it's very clear that we separated the two colors or the two sections from each other. Okay. Now, can we do this convolution process naturally, or we always need to do program to convolute filter with the image? Actually, the concept of convolution included long time ago. Even before we use the computers to process the data. Like, I'm very sure that most of you saw this type of filter that added to the cameras. So adding a filter, so this is a paper actually, just a piece of paper. If we add this piece of paper to the image or to the camera, when after we close this size a little bit, we can have this view. So this is just a convolution between this and the filter. Okay, I'm not sure if any of you saw videos recorded in the 70s or the early 80s, but most of the videos used in events, they try to use this technique. They added some filter to the lens to generate the output like this. So we can extract filters to do some specific actions in the image. Like what? If I have video, and this video actually produced from a shaky camera. While I'm moving, I'm holding my phone like this or my camera like this, and I'm running with it. I can extract the filter pattern for this shaking process. Then I can remove it from the image. So this is the shaky version. And after processing, we found that this is the filter that caused the shaking. So if we convolute this with this, we can have a shaky version. So we can reproduce the same effect for any given image or any given video later. Okay? The good news is now most of this process happen or occur through neural system. Okay? So we don't have to do this convolution process ourselves or using the for loops, as you will see in a second. Everything now can be occur or can happen through the convolutional neural network because it has a convolution process occur inside. We'll come again to this point later. Okay? Now, one of the technique also we are using for the images is the thresholding. So I can have a given image, then if the image is greater than some specific threshold, I will give it 1 or white. If it's below this specific threshold, I will give it 0 or black. Now, does this technique consider to be a linear filter? We learned about the linear filter at the beginning when we understand the convolution process, right? Let me give you the definition back. Yeah. We're calling the cross correlation and of course the convolution as a linear filter because we are replacing each pixel by a linear combination of its neighbors. Right? When we apply the filter and place, we sum all of those weighted sum to produce the output. Now, that's why we call it linear. Remember? Now, does the thresholding process consider to be linear as well?
Explain the threshold process.
The threshold process means for this image, I will go over all the pixels step by step or pixel by pixel. If the pixel is greater than specific threshold, I will add in the output 1 or 255. If it's lower than, I will add 0.
You are going one by one.
Yes.
So it's similar to linear.
Do you think this considered to be linear?
No.
Who said no? Only 2 votes. How about the rest? Who said yes? Don't worry, I'm not giving negative. I'm always give bonus. So if you say a good thing, you will get bonus. But you will not get negative if you said the wrong thing, because we are learning now. But then the exam, you will get 0 for them. Is it linear or no?
Not linear.
Okay, I got your opinion. I'm now asking the rest. Who agrees it's no? Who agree with yes? Okay. Let's come back to the definition of linearity, as we stated last time. What is the definition of linearity?
Linear neighborhood.
This is the definition of linearity. If any function satisfies those 2 conditions, we consider it as a linear function. If none of them or any of them or one of them does not satisfy, we doesn't consider this function linear. Now, look at this. If you try to plot it, if this is the input, the input is below the threshold A, the output is 0. if the input above the threshold of A, the output will be 255. Does it look linear for you? So this is not a linear operation. Okay? Linear operation looks like this. Okay? Which satisfy those two conditions. This one, if you try to apply any of those conditions over it, it will fail for both. Okay? So this is not a linear operation. That's why we are trying to avoid the threshold in some cases. And that's why we use it in some cases. So if you combine convolution plus thresholding, we are going from the linearity part to a nonlinear part. Okay? Which is exactly what we will do in the neural network, as you will see later. Okay? So put this in your brain. When we are using the thresholding, we are removing the linearity. Okay? That's why we will need it at some points. Okay. Now let's see how we can apply the code for this convolution process. Okay. So we will start, or we'll do the example that we did in the lecture. Which example? If I put again. We will do this example. A very simple example. We have image of size 10 by 10, and we have a filter of size 3 by 3 of dimension, of the elements, all ones, 1/9, and this should be the expected output. Okay? The input size is 10 by 10, the output size should be what?
9 by 9.
9 by 9. Okay? So we will create the input image ourselves. So we'll start by creating an empty matrix of size 10 by 10. Empty. All filled with zeros. Then we will add 90s on this place, which is 5 by 5. 5 and 5. Actually, let me move it here. See? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 5 by 5. So I'm generating small matrix inside, which is 5 by 5. All filled with 9s, except this 0 in the middle. So in the code, I'm generating 5 by 5 matrix, all of them 9s. Then for this one, I'm adding the 0 in the middle. Finally, I will add this 90 matrices or matrix inside the bigger matrix. And we'll add the final 90 that we have aside. This final 90 that's here by itself. Okay? So if you look to this is 0 and 0. This point is 0, 1, 2, 0, 1, 2, 3. So the start point here is 2 and 3. Okay? Then this point is 8 by 2. Okay? So go back to the code. Eight by 2 is 90, and this is from 2 to 7, and this is from 3 to 8. Okay? Now I created my matrix or my image. I'm printing it to check the result. So let me comment those parts. Here it is. Actually, let me make it bigger. Can you see it? Can you see it or you need a magnifier?
Zoom is okay.
I can zoom, but I can magnify. Okay? So you see, it's show the magnifier, destroy the shape. So starting from the same position at the required one, and here we have the 9 down version. Okay? Where are the magnifiers? Where are the magnifiers? Okay, so now I created the matrix that we work with. Next step, we need to create the filter. So the filter will be a 2D array that all of them filled with 1 by 1, 1 by 9, 1 by 9, 1 by 9. Okay, so row 1, row 2, row 3. Each one of them consists of 3 columns. Okay. Finally, I have to create the result matrix. Why? Because I will receive the output in this result matrix. I'm creating it with the size 10 by 10, similar to the input. If I have any extra thing from the sides, I will keep it to be filled with zeros. So I'm starting the result with a 0 array of the size 10 by 10. Then I will start to do the convolution process. How the convolution will look like? First, as I told you before, what's the difference between convolution and the cross correlation? The flipping. So if I receive the filter, the first thing I have to do with the filter is flipping it horizontally and vertically. If you remove this step, you are using cross correlation. Okay, so this is the only step that distinguishes between cross correlation and convolution. Okay, second, I have to determine the shape of the input and the shape of the kernel. Why? Remember the equation? Remember this equation? To estimate the size of the output, I need the input size, the filter size, the padding, and the stride. So I have to include this into my problem. So extract the shape of the filter, the shape of the input. The padding and the stride will be applied as parameter. So it's optional. I can change them if I want. By default, if I don't change them, the padding is 1, the stride is 1. What is the meaning of that the padding is 1? The output will be 9 by 9 if the padding is 1. What is the effect of the padding?
To add one layer to the sides.
So if I have padding of 1, the output will be 9 by 9? No. It will be the same as the input. So it will be 10 by 10. Because after adding the padding, the input will be 12 by 12. Focus. Adding the extra pixel for the padding will change or convert the 10 by 10 to 12 by 12. Okay? So in this case, the output will be 10 by 10. Here I'm using a stride of 1, which is the default stride value. Again, if you change it, it will affect the value here. As you can see, here I'm building the equation that I shall just show you. Right? Input, kernel, plus 2 padding over stride plus 1. And because this one can produce fraction, in this case I have to be what? To cast, to make sure that the output will be integer. Okay? In case we received fraction, it will cast it or round it to be integer value. Then I'm creating output with this given size. Okay? Then I will add small condition if the padding is 0. So if you are using 0 padding, then the output will equal, the padded image will be the exact image. If I add a pad, in this case, I have to add the extra zeros around the input image. Those extra zeros here, I'm considering them as zeros. So no wrapping, no flipping, no reflection. Then I will start the convolution process. As you can see, the convolution process itself is just what? One line of code. I iterate over all the input images with the step of the stride, 1 pixel, 2 pixel, 3 pixel, depending on the stride value. And for each step, multiply and sum. Multiply all pixels from the filter to the pixel of the corresponding image and sum. Multiply, sum, add. Multiply, sum, add. That's it. Okay? This will be my output. Okay? Now, unfortunately, this operation will result in a floating point out. We are multiplying with fractions and adding and do so many mathematical operations. Even if those numbers are integer, the output will be float. Now, can the pixel value in the image be float? It's always integer. We have specific gray levels or specific color levels. It can't be float. So we need to make sure that we are casting it to unsigned integer. Okay, so this casting step is very important. You can do it here or do it here. Either way, here or there. But you have to make sure that the output of the convolution process still a valid image. Okay? Then we can show this as an image or as a matrix. So here we are showing it as a matrix format. Here is the output. Okay? As you can see, because I added the extra padding, I had this extra value back there. In the original problem, I didn't add this extra pad, right? So that's why the last one become 0. Here, I add this padding, now I have a value down there. Okay? Is it clear? Now, you can change the values in this code however you would like with any filter you would like. So you can read a regular image from here, then apply the operational filtering exactly like this. Okay? Is this clear? Any problem? Any questions? Okay, so I think you are ready now for assignment 2. After we finish the second part today, actually let's take 10 minutes break, then we'll come back, we'll continue. Okay, so far we learned how we can do the convolution process and why we need to do the convolution process. Can you refresh my memory? Why do we need the convolution process?
Enhancement of the image.
For what?
Enhancement of the image.
Okay. So this enhancement can't be occurred using the traditional technique that we had before, like alpha or or gamma. This enhancement can occur using this technique or the histogram equalization.
Yeah.
Can?
We use filter.
So can we use the alpha beta technique or the gamma technique or the histogram equalization to solve this anti-aliasing problem? Can we? So at the end of the day, the function or the tools provided by the convolution can help us solve some problem that can't be solved using the traditional image enhancement technique. Like this problem, if you recall from the beginning, why it occurs, why we have this aliasing problem? Because the sensor in the camera has some area with the optical sensor and missing the optical place, the other places are missed. So no sensors here, no sensor here. The optical sensors included on almost 50% of the chip. Okay. Now this missing area will cause the data to be sampled like this. That's why we need a filter to solve this problem. And now we learn that the filter is what? A convolution process. Okay? Now, if you look to these lines, those lines are what? Edges, right? And we stated before the break that the edges are what? High frequency or low frequency? Who agrees high frequency? Who agrees low frequency? Who need a blanket? Come on. It's high frequency components. So those are high frequency components. Okay? That's why we need to remove those high frequency components to have a smooth image. So we need to have low pass filter. So the anti-aliasing filter is nothing but a low pass filter. Okay? What is the best low pass filter we learned about so far? The Gaussian filter. Okay? Is it clean? I don't want you to lose the main purpose of what we are doing. Okay. Now, if we go to the same problem back, now we learned about all those convolution process. Again, in the presentation, I'm giving you some extra resources in case you want to learn more about the Fourier analysis. So this is a link. If you want to test some convolution or some demo, okay, this is available online. And also there are some video resources for this channel, which called 3 brown, 1 blue, 3 blue, 1 brown. It's specialized in explanation of high-end mathematics and AI systems, okay? So they provide some good examples or some good explanation about the Fourier analysis in general, including the Fourier series and the Fourier transform. Okay? Now, assume that I'm giving you now an image, and I ask you to give me a smaller version from this image. What exactly you will do?
Move some pixels.
What?
Remove some pixels.
Remove some pixels. Okay. So you are saying, for example, if I want to reduce the size of this by half, and the pixels looks like this, I will choose this, drop this, choose this, drop this, choose this, drop this, and that's so on, right?
We can check for the same pixels, like which have the same values, and we can remove one
My
of
question is clear. I want an image or version from this, which is half size. How can you do that?
You filter it without adding padding.
Okay, if I do this, in this case, I'm removing almost 1 pixel or 2, 3 pixels from the sides, right? If this will reduce it by half, it will reduce it, yes, but is it by half? You can keep doing it multiple times like this. Okay,
More efficient way.
so for that purpose, we need to learn about something called sampling. Remember the sampling problem that we discussed last time? If I have a signal, I want to get samples from it.
Yeah.
Okay, we want to do the same thing here. Assuming that I have image and I want to sample it to produce a lower version of it. But with one condition, I should be able to retrieve this one back with a decent quality. Meaning, if I try to put this back to the same size, it should be decent quality, not bad, not completely destroyed. How can this occur? One of the technique is the technique you proposed. I can take one pixel and ignore the next one. So take this, ignore the next. And go like this. In this case, we can sample this to the lower one, but if you try to put this smaller size back to the original one, it will be completely blurry. As you can see, this version, as an example, is completely destroyed. Okay? So, can we do some technique that can approximate this process and make it more efficiently for the sampling? They said, yes. How? Remember the problem? We got this and ignore the next one. Got this, ignore the next one. This is exactly typical or similar to the problem I just explained of the sensor, which has one sensor here, space here. One sensor here, space here. One sensor here, space here. So this sampling issue is exactly similar to the sampling problem occurred at the camera sensor. How we solved this problem?
Filter.
The anti-aliasing filter. So we will do the same thing here. So first, we will filter this image to generate a newer version with almost the same size, but the pixel value is an average between it and its neighbor. In this case, if I sample, I will choose a pixel which has information about the neighbors. Not only pixel which oscillate by itself, no. The pixel value that I will sample will have some information about the neighbor. In this case, if I want to retrieve it back, I can approximate the value of the neighbor. So if you are sampling correctly, you will not have this problem. You see this? The same problem of the aliasing. And this can be more clear in graphics. Do you see this line? Is it going straight? If this one goes straight, if this one goes straight, you see, it starts to have zigzags and unacceptable shape. So this sampling issue or this sampling problem considered to be a bigger problem, especially when we start to go with synthetic data. Again, how we will solve this? Same thing as we stated here. First, we will start by filter this, then sample it. So this is a filtered image. Why it's filtered? Again, the pixel after the filter will include information about its neighbors. So this way, I will guarantee that the pixel value will be a sample, a good representation for its neighbors. Then if I want to get more or reduce it more, in this case, I have to make a Gaussian filter to this as well, then sample again. Then apply a Gaussian filter here and sample again, and can do this again and again and again. You put this one back up, that's how it will look like. Again, compare this to this. See this? It's wrong. This is the Gaussian version. This is the non-Gaussian. See? This one is so smooth. This one is pixelized. Okay? So the Gaussian filtering before the sampling can solve this problem. Actually, there is a mathematical explanation for this part. Okay? Again, I don't want to take lots of time explaining this, but I will leave you the slides to read about this. Again, it's similar to the concept we discussed before for
So,
the best sampling, the best technique for sampling. When we said that if I want to sample this signal, we said that the sampling frequency should equal what?
when you're looking for a math thing right now, or?
The sampling frequency for the signal must be double, at least double the maximum frequency I have for this input signal, okay? To avoid the aliasing, okay? Which we are calling it the Nyquist rate. We discussed this last week, very quickly, okay? That's why we need to make sure that we are sampling, we are taking relation between this pixel and the neighbor to avoid this aliasing and get some information and remove the high frequency component that will cause problem during the sampling, okay? Now, this technique, or this process that we are doing right now, actually it's called a very fancy name. What is this name? It's named Gaussian pyramid. What is the Gaussian pyramid? Gaussian pyramid say, if I start with an image, then I apply a Gaussian filter to it, then sample it, then apply Gaussian filter again, then sample it again, then apply Gaussian filter again, and sample again, and keep doing this again and again and again and again. The version that we got here called Gaussian pyramid. So the Gaussian pyramid is a multi-level version from the image, including the original one. So this one, which has all the edges. Plus smaller size versions, which is sampled after blurring. So blur, sample, blur, sample. Blur, sample, blur, sample, blur, sample, blur, sample, until we arrive to the pyramid. So it's a multi-scale version of the image that we can use to have many sizes of the given image data. Why this is good? Why this is important? Actually, this Gaussian pyramid is so important in many applications. One of them, if I'm looking for objects on the distance, assume that you have image which has someone taking selfie, and has some other persons on the back. Something like this. Couple. Now, I'm now trying to search for the images in this, sorry, in the search for the faces in this image. Now, what is this face size? Let's say 120 by 120 pixels. what is this face size? Let's say, let's check this. This one is 10 by 10. Now, if I'm designing an algorithm to find the face in this image, will I be able to find the 10 by 10 or the 30 by 30 or the 60 by 60 or the 120 by 120? Each one of them different size, and each one of them has different property. The eyes here, large, nose, large, hair, large, here, less details, here, less details, here, less details. Now, I can theoretically design the filter to search for the smallest value, which is this one, which is 10 by 10. So I will design the detector to search for this small value. Then I will create a pyramid from this image. In the first level, it will be able to find the smaller one because it's within the range 10 by 10. After I found the next scale, it will be able to find the 30 by 30. After the second level, it will be able to find the 60 by 60. After the third level, it will be able to find the 120 by 120. So I'm designing the filter or designing the algorithm right now on the smallest size. Then after applying the filter, all large objects will become what? Small. So I will search for the smaller one on all the levels. That's why we call it a multi-scale pyramid, because it can provide version from the images or the components or the object inside the image on level different scales. And this is one of the most important technique we are using in the computer vision and the image processing. And if you start to work with the neural system, you will see that in most cases, not all, in most cases, we are building a multi-scale version from the image before applying it to the neural model. Okay? So the Gaussian pyramid considered to be one of the essential components or essential technique that we are using for the object detection and for the subsampling algorithms. How we can build it? I will start with the original image, then apply the kernel to blur it, then sample, then another version, sample, another version, sample, and keep doing this until we build the levels of the image we would like. Okay? Now this algorithm or this technique is new. Actually, no, it's old. It started or introduced by 1983, but it proved to be very efficient in many applications of the computer vision. We are still, as I said, using it until the moment in many applications. Okay? Now, can we use it also for synthetic data? Remember the problem we discussed here? When we have synthetic data, every time we are going to the back, you are reducing the number of pixels. So this one has large number of pixels. Going back, you are sampling it. Going back, you are sampling, until some point you will find that the sampling is destroyed. Now, can we use the Gaussian filter before the sampling? The answer is yes. And if we did this, that's what we will have. So this is without the Gaussian filter, and this is with the Gaussian filter. You see, it starts with big, going small, until what? Vanishing. Here, it's not vanishing. It becomes like what? Like a noise. Okay? So this part is meaningless, doesn't have any meaning. For actual world, we have a vanishing point, right? If you study architecture, they will tell you that all the horizontal lines, when it intercept in what? The vanishing point in the horizon. Okay? So all those lines will intercept in the vanishing point of the horizon. You'll find something, nothing there. Okay? So this technique is working well if we want to make subsampling for the given data. Okay? Now the question is, can I play the game on the opposite direction? What does this mean? Can I have small size image and produce higher size one? Remember, if I have bigger one and I have a smaller one, this is called a subsampling. Now I'm having the smaller one and I want a higher version. Can I do that? Can we do this trick?
I think the final image will not have a decent image.
I'm sorry?
The final output that we'll have from that procedure, it will not be a decent image.
Can we have a decent image? The answer is yes, we can. And to do this, or this problem in the computer vision called super resolution. So I'm starting with a small image with a smaller size, and the required output is an image for the same scene or for the same view, which has larger number of pixels. As an example, I want to start with an image of size, let's say 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 7. 7 by 7. I want to end up by an image 20 by 20 for the same exact scene. This is similar to what? Zooming. As if you are zooming for the image. Now, if you have a magnifier and you are zooming over some reading, will you lose the resolution? Why? You have a magnifier. You know the magnifier? And I have a book. And I put the magnifier over the book letters. Will I lose the resolution? Why? Remember the concept of the camera again. Naturally, how many rays we are receiving from the environment? Infinite. Okay, so I'm receiving so many rays. So if you have an actual magnifier, the number of rays come to the book and reflect to the magnifier, to your eyes, infinite. So if you put it, you receive image with the same exact resolution as if you are looking with your eye, because it's an optical zoom. Okay? Now, do we have the same image or the same concept with that digital image? The answer is no. I have the pixel value at some specific region, pixel value at some specific region, and I want to estimate the pixel value here. And can we translate this word estimate? In mathematics, that's called interpolation. Oh, I'm having specific value for the function or for the image, and I want to guess those intermediate one. How can I do that? One of the technique is called nearest neighborhood interpolation. What is the meaning of nearest neighborhood interpolation? Nearest neighborhood interpolation say simply, I will start from this position and this value will continue with me until I arrive to the next sample. So it will go like this. All this value will be with this range. Then after I'm going here, I'll continue with this value until I arrive here. Then for this, I'll continue like this. Then for this, I'll continue like this. Then like this, and so on. So that's what we call nearest neighborhood. So the value of the neighborhood will have the value of the nearest sample. Okay? This produce a decent function for me? Answer is no, of course not. Because the value between this and this, 100%, it was not that fixed. So if you want to see how this will affect the image, look to this. So now I'm using the nearest neighborhood to magnify this to this. So all those values are similar. All those values are similar. All those are similar. All those are similar, and so on. But is this a good thing or a bad thing? Of course, bad thing. I destroyed the details. Okay? Now we destroyed the details. Now, can we improve this quality or the quality of this problem a little bit? They said yes. To understand this, let's go to the original problem. Assume that we have this original function and we are sampling it. Sampling means I'm choosing specific value of y at specific x value. So I'm getting the value at 1, at 2, at 3, at 4, at 5. I'm not getting any value in the middle. Now, if I want to go back to the original value from this to this, I need to estimate those in the middle. Now, the technique of the regular nearest neighborhood didn't work well. Some people say, okay, how about using a linear? What does this mean? Means I will consider this value in the middle as if it's a linear connection between this. So I will build the line between 1 and 2 and estimate the value in the middle at 1.5. Build the line between 2 and 3 and estimate the value at 2.5. Between 3 and 4 and estimate the value of 3.5, and so on. This is good. But how many lines I have to build to do this? Count how many samples equal the number of lines. Does this make sense? No. That's why we replace this with a different technique. What is this technique? They said, instead of building a line between the sample, I will convolute it with triangle. Remind me again, what are the convolutions doing? What is the convolution process? I have a filter. I flip it horizontally and vertically here. This is one size because this is 1D. Then I will cross correlate it with the image. What is the meaning of cross correlation? Multiply and add. Now, if I want to find the convolution between this pyramid or this triangle and this function, let me mark this with red. I'm not sure why this has been wrong. What's going on? Every time it's draw again, I'm not sure why. Anyway, so if I want to convolute this with the green function, what's wrong now? You know what? Let me stop. Let's see. So make sure that none of this will happen. Yeah. So this is the green, sorry, the red core, and this is the function I want to convolute with. First step, this is the filter. I will flip it horizontal only because I don't have vertical here. Okay, so flip it. It's symmetric, so it will cause nothing. Second, multiply this red to all the green points. Now, 1 times 0 will equal what?
Yeah.
This is 1 and this is 0. This 1 also times 0. This is 0 also, and this is 2. So all this are zeros. Now, the point of the middle. The maximum value here is 1. So the middle value here is what? Half. So I will multiply half times 2. 1. Half times 1, or 1.5. So half times 4/3, or 1.5. So 5/2, or 3/2, sorry. Three over 2, which is 1.5. This will equal the approximated value between this. So if this is 2 and this is 1.5, the approximated value will be the point on the middle here, which is 4/4 plus 3/4, which equal 7/4, which is 1 3/4, which is the middle point here. Try to find the line between those 2 points and find the middle point. You'll find that it's the same exact value. Okay? So the convolution process between this filter and those sample produce value similar to building a line between those. Now move this here in the middle. It will give you the value here exactly in the middle. Move this here in the middle. It will give you the value here exactly in the middle, and so on. So this filter can build linear function. And what I'm doing is what is a convolution process. Did I build any line between them? No, just a regular convolution, similar to the convolution process we covered. Okay. Now, does this linear convolution will work well with images? And if I did so, how I can reconstruct the higher dimension version? They said it's very easy. First, assume that I have smaller image of size 4x4. And I want to make it bigger. With the size 8x8. Okay? Now, assume those pixels are how can I convert this into this bigger size? They said, first, move each one here to the corresponding place here. How? They said the one in the corner moved in the corner. Then skip and put the next. Then skip, put the next. Then skip, put the next. Then for the next one, skip, put the next. Do the same thing. Now, how can I fill those gaps? They said by applying an interpolation filter. So I will apply a filter here on those to estimate this one in the middle. Shift it, apply it here to estimate this one. Shift it, apply it here to estimate this one, and go on. This way I will fill the missing parts. That's exactly similar to what we have here. Okay? Now, this filter is 1D, which has 1 in the middle, 0 outside, and half on the edge. Can we do the same thing here? The answer is yes. I can design a filter which has 1 in the middle, 0 or half, depending on however I want to make it, and 0 on the side. Okay? And based on that, I can adjust those weights. Okay? Now, whatever we did like right now is linear interpolation. In the linear interpolation, the best way to approximate this one, this is the original function, by the way. So, if this, the best way to approximate this, the answer is no. We have different technique. Like what they or they prove that the best filter that can reconstruct or make an ideal interpolation is the sync filter. Remember, what is the sync? Sin x over x. This is the best filter to reconstruct the sample back. But the problem with this filter is not practical. If I find a window like this, this means I'm ignoring some components. because those sides go to infinity. They are not stopping. Okay? So if I find or use part of it, I will ignore bigger part. So I can't use this one. That's impossible. This one is the boxy filter, remember it? Which will cause the nearest neighborhood interpolation. The linear interpolation will make it look like this. Again, it's not the best. They said, let's design or let's try the Gaussian one. They found that the Gaussian one give a good approximation to the original. But it's not the best. The best one is what? The sync. The Gaussian is okay, but it's not the best. What is the difference between this and this? Look to this kernel and look to this kernel. What is the difference between them?
Is placed in between that and it's continuous.
This one has maximum here, this one has almost maximum here. This one going smooth this way, this one going smooth this way. The main difference that this one go to the negative part here. Does this one go to the negative part? It always go positive. Can we have a filter that go to the negative part to simulate this as much as we can? He said yes. And we call this filter a bicubic. So this bicubic interpolation considered to be the best filter that approximate the sync. Okay, so it's the best one we can achieve. Is it the best we can, or is it the best one to approximate the so to find the exact function? No. The best one to find the exact function is the sync, but it's unpractical. The best practical one is the bicubic. Okay, so for the images, we can have the bilinear, which is just a linear, or the bicubic, which is like the sync, which means it has negative parts here, but with no edges. What is the equation for the bilinear? Sorry, bicubic. This is the equation. So the equation is not a friendly equation, unfortunately. Okay? Now, if we use the nearest neighborhood on the image and the bilinear and the bicubic, which one looks better? This one is too pixelized. This one is okay, but it's still some pixelization places. This one is so smooth. Okay? We use this technique only for super resolution. The answer is no. We can use it in other applications. Like what? Like if we want to convert the image from 2D into 3D. We will come to this transformation at some point later in the course, where we can move this and give it depth. In this case, those pixels that we generate for the depth need to be interpolated, because I don't have them here. This is regular 2D. How I convert it to a 3D image? I need to generate this depth data. So we can use this interpolation technique as well. So this technique is a very well known for so many applications. And based on those techniques, they generated something called the vector image. Did anyone hear about the vector image or the vector representation? Anyone work with Adobe AI? No? It's not AI, which means artificial intelligence, no.
Creative Cloud.
Yes. So there is another technique to save the image using or as a vector. In this case, we can keep the edges so sharp without any loss. But in this case, it will not be pixels. I can't read it the same way. Okay? There are techniques to convert from this to this and return back. But again, we will not go within this in our work. In many applications, especially when you are having icons or characters, we can regenerate a newer version from the image using this vectorizing and super resolution technique. Okay? Actually, there is a separate field in the machine learning and the computer vision for the super resolution because it has so many critical applications from the satellite images to sensitive applications. And most of you have it now, have similar algorithms on your phones. When you hold your phone and you take a picture, if you start the camera and you're gonna take a picture, then you are zooming. When you will see down there, you will see a digital zoom. This is not an analog zoom or optical zoom, okay? This means I'm generating higher version from the image more than the capacity of your optical sensor here. This interpolation that happened in the image occur using the same technique, okay? But nowadays, as I said, we are using the neural system for this job. So now there are some network which called super resolution CNN. This is considered to be an old technique actually. There are super resolution GAN, which is also now all considered to be old. There are some other super resolution technique using transformers, which work much better than all those one. Good thing that we can now run all those algorithms on our computer or our phones using some technique called NPU, Neural Processing Unit. Small tiny processor or coprocessor added to your computer board or your phone board, which can do all those tasks to you. So in many phones right now, you can have this smart detection for the image to avoid any shaking in the image. This is included now in your phone and can run on your coprocessor, okay? Or it can be used for smart cropping or alignment or any of those applications. So those now become a trivial thing to do or to have on your phone, okay? Any questions? Now, how can we do this on code? So we'll start by a simple case. Assume that we have small image for baboon. You know the baboon? It's a kind of apes or monkeys. Okay. This image is low resolution. So if you show the original dimension for the image, what is the dimension of this image?
2 by 250.
What?
250 by 250.
Actually, it's 256 by 256. Okay. Again, I told you you can't find the dimension from the figure. That's why don't use the figure to save the image. Sweet. Okay. Now, I want to convert this image to another version, which is 512 by 512. Okay? How I will do that? First, I will start by generating another version from the image, which is filled by zeros. So I want this image to be 512 by 512. So I'm having a newer image, which has double the height and double the width, which is 512 by 512. And don't forget that this image should be 3 layers because it's color image. So it has to be the same number of channels. Then I will add the original image inside this 0 ones using the same technique. Add 1, skip 1, add 1, skip 1, and keep doing this in all image. You can do this in one line exactly like I'm doing. So start from 0 with a step of 2 until you arrive to the 2H. So this is the starting point, this is the ending point, and this is the step of 2. Same thing here. Then I will apply a super resolution technique over the image. This super resolution technique is nothing but applying the convolution filter over it with a filter from my choice. Actually, the filter is here. This is the filter that I'm applying to the image. As you can see, it has 4 in the middle, 2 on this side, 2 on the other side, 1 on the corners. Okay? Then I'm dividing all the parts by 4. Why? To make sure that the middle part is 1. Remember. Remember here, this part must be 1, and those sides must be half. So 1 and half. Okay? That's why I'm applying 4 in the middle and divide everything over 4. Then I'm doing 2D convolution with that filter over the image. I have to keep doing this over the 3 channels to generate super resolution on the 3 channels. If I do this, that's what I will receive. Again, the convolution up there is exactly similar to the convolution process we have in the other convolution code. No difference. This is the output, and this is the input. As you can see, they are exactly similar to each other. So this is a super resolution version from this. This is 256 by 256. This one is 512 by 512. That's why I'm giving you or showing the ruler or the axes to see which one of them is bigger. But this view can't show you nothing, or you can't prove that this is bigger than this. The only way to can see this is by seeing the saved version on your computer. So if I open So those are different versions. So this is the original Papoon image. Okay. This is the smaller version, and this is the magnified version. You see the difference now? Can you see this in the screen or the IM show? No, you can't. Okay, that's why never save the screen or save the figure from the IM show. Okay, is it clear? Any questions? Any problems? Okay, you take the attendance and you'll be all set to go.